In this video we want to consider reciprocal functions, and so we'll start with the definition and we'll do an example, consider some features, and then another example after that. So definition of a reciprocal function, well, if y equals f of x is a polynomial of some description, then its reciprocal function is simply y equals 1 over f of x. So just like with fractions, we would say that the reciprocal of, the fraction 2/3. So if we had a fraction like 2/3, we could say, well, the reciprocal of that is 1 over 2/3, which is equal to 3 on 2. So it is with functions as well. So let's start off, like I say, by actually considering a specific example and think about what it looks like, and then we'll talk about some more general features. So I'm going to pick one from exercise 12b. In fact, let's pick the very first one here. So this one says to sketch the graph of y equals f of x and y equals 1 on f of x on the same set of axes. And we're going to try that for the function f of x equals x plus 3. Alright, so our first job then would be just to sketch the graph of y equals x plus 3. So let's start off by doing that. Try ourselves a set of axes here. Now x plus 3, so there's y, there's x. So x plus 3 has a y-intercept of 3, its x-intercept would be -3, so it would be the function something like that there. So there's y equals x plus 3. Okay, so using that, let's analyze what the graph of y equals 1 over x plus 3 is going to look like. And I suppose the first thing that we might notice is that where x plus 3 is equal to 0, 1 over x plus 3 is going to be undefined. So that occurs at the x-intercept here at x equals -3. That's where x plus 3 is equal to 0. And so what that means is that there's going to be a vertical asymptote. So that's x equals -3. That's going to be a place where the reciprocal function is undefined. So let's think about what the value of 1 over x plus 3 is doing as we sort of move away from that asymptote. Well, we could consider the specific value when x is equal to 0. So when x is equal to 0, 1 over x plus 3 is equal to 1 over 0 plus 3, or 1/3. So in other words, when the y-intercept of the original function is 3, then, or when the value of x plus 3 is 3, the value of 1 over x plus 3 is going to be 1/3. So that's going to be the y-intercept of the reciprocal. Now, as we move away from the asymptote, so let's say as our values of x, as we're moving away from the asymptote, the vertical asymptote in that direction there. So I should just make clear that we understand the word that I'm saying there. So asymptote. The P is pretty much silent there, and asymptote, I guess a sort of fairly casual definition of that would just be a line that the graph approaches but never touches. So as we go away from the asymptote, the vertical asymptote in this direction, as our values of x are increasing from there, the value of the function is getting bigger and bigger, isn't it? So the function, the value of y, is going up, which means the value of 1 over that is going to be decreasing. As we go down this way, the value of y is getting smaller and smaller, and so as y gets towards 0, 1 over that is going to be becoming a larger and larger value. And therefore, that means that the function is actually, or the reciprocal function is actually going to be approaching the asymptote. So it's actually going to be going towards infinity as it gets near that asymptote, and it's going to be going towards 0 as x gets bigger and bigger. So as the function is itself, x plus 3 is increasing, getting bigger and bigger, then 1 divided by that number must be getting smaller and smaller, going towards 0. But it's never going to be negative, is it? Because x plus 3 is always positive. As these values get bigger and bigger, more and larger, they're always positive, and therefore 1 divided by that is always going to be positive as well. But it's just going to be getting closer and closer to 0. Now, I haven't given myself too much space on the other side of the asymptote, but for all of these, well, these values of x along here, x plus 3 is a negative number. Therefore, 1 divided by that has to be a negative number as well. And so if we use that same sort of logic, we should be able to see that the function's doing a similar thing, or the reciprocal's doing a sort of similar thing on this side here, where as we go towards the asymptote, so as values of x go towards this asymptote, they're actually getting closer and closer to 0, and so therefore 1 divided by that is becoming a more and more negative number. But as the values of the function sort of get more and more negative, they're actually decreasing, but we can think of them as sort of larger and larger negative numbers. Therefore, 1 divided by that is getting closer and closer to 0, but always negative. Okay, always negative. So let me get rid of a few of these other things that I've put on here just so we can see the actual function itself. If I can get rid of that one without deleting the whole thing. No, didn't think so. Alright, so there's our function x plus 3, our original function x plus 3, and also our reciprocal function y equals 1 over x plus 3. Alright, so what we're going to do now is consider some sort of general features, the things that we talked about just then. Alright, so let's think about some of the features that we've already seen from just doing this one graph here. So first of all, as the original function is increasing, its reciprocal will be decreasing, and vice versa. So as this function here was going up in value, its reciprocal was coming down in value, and likewise as it was going down in value, either as a positive, then it was going up in positive values, or here where it's decreasing as a negative, then this is increasing as a negative value, and so on. So basically the function and its reciprocal behave in opposite ways in terms of increasing and decreasing. Next one is to say that where the function is positive, its reciprocal is positive, so 1 divided by a positive number is still positive, and likewise if f of x is negative, then its reciprocal will also be negative. So 1 divided by a negative number is still a negative number. And where the function is equal to 0, that means its reciprocal is undefined, isn't it? So basically wherever the original function has an x-intercept, that means that the reciprocal function, the graph of the reciprocal function, will have a vertical asymptote. It'll be undefined at that point. Alright, now a couple of features that we haven't considered here, because we were graphing a linear function which didn't have any turning points or maximum or minimum values, local max or min values, we didn't consider these two. But let's think about the fact that if the original function, has a local maximum at a particular value of x, then that's the point where its reciprocal will have a local minimum. And that relates to the idea of increasing and decreasing. So I guess if we're saying that, f of x, actually we'll do an example to demonstrate that, I think is the best thing. And likewise, if the original function has a local minimum at a particular value of x, then its reciprocal will have a local maximum at that point. Because either side of a local minimum, think about this, either side of a local minimum, the function is increasing, which means either side of that particular value of x, the reciprocal will be decreasing. So somewhere along that same value of x, the reciprocal must have a local maximum. So let's sort of look at a different example that might help us to demonstrate that last one there. And so let's consider, where are we? Question 1. We're still in that same exercise, and part E was f of x equals 4 minus x squared. So I want to graph that and also its reciprocal. So 4 minus x squared is a parabola. Let's try and draw a parabola here. Alright, a parabola which has a y-intercept of 4. I haven't drawn it terribly symmetrically, but I think it'll suffice. There's y, there's x. So 4 minus x squared has a y-intercept of positive 4, and its x-intercepts are plus and minus 2, aren't they? So negative 2 and positive 2. So let's straight away say, well, if we're going to graph 1 over 4 minus x squared, so this here is the graph of y equals 4 take x squared. Well, first of all, we're going to need asymptotes, vertical asymptotes at these. So where the original function had zeros, the reciprocal is going to be undefined, so there'll be vertical asymptotes. Likewise, we know if the original function had a value of 4 at this point here, so when x equals 0, then the reciprocal will be 1 over 4. So it'll have a y-intercept of 1/4. Alright, so that's what's happening there. Now what about either side of these asymptotes? Well, in between the two asymptotes, so in between there and there, the original function is always positive, isn't it? So that means the reciprocal will be always positive there. And because it's decreasing as we go towards both of those asymptotes, that means its reciprocal will be increasing. So as we go away from that y-intercept there, we're going to see that it's increasing towards those asymptotes. Let me get rid of those arrows there. So the reciprocal function is going to be increasing and then approaching infinity as the original function approaches 0. Outside those two asymptotes, the original function is negative, and as we go this way here, it is decreasing. So therefore, in other words, it's going down, it's getting less and less, isn't it? Decreasing. So the reciprocal function must be increasing. It must be going up towards 0 here. So we're going to get that sort of, it wasn't a terribly fluid sort of curve there. And on the other side of the other asymptote, it's going to kind of be like a reflection of that. Alright, so let's get rid of that arrow there, and say that's going to be our graph of y equals 1 over 4 minus x squared. Now that one there demonstrates that final property as well, the one where we said if the original function has a local maximum at a particular value of x, then, so this one here, if f of x has a local max at x equals a, then 1 over f of x will have a local minimum. So the original function had a local maximum at x equals 0, and our reciprocal function had a local minimum at x equals 0.